Hello, welcome to the lecture series on power system operation and control. In this session, I would like to give introduction to power system operation, economic dispatch, and we'll finally discuss the first case one of economic dispatch. Here is the overview of the series. Power system operation and control is classified into two categories: power system operation and power system control. Power system operation is further classified into three topics: economic dispatch, unit commitment, and hydrothermal scheduling. The power system control, on the other hand, deals with frequency control and voltage control. Basically, power system operation involves transfer of electric energy from generating stations to the consumers through ensuring safety, quality, reliability, and economy. You know the power production process in a thermal power plant. In this particular session, we are discussing about power system operation of thermal plants. A thermal plant basically consists of a boiler, turbine, and generator combination working to produce power at 11 kV basically. So, how this power has to be shared among the available units is the concept of economic dispatch. For a given load, how the load sharing has to be done among the available units. So we are having three terms here: economic dispatch, unit commitment, and hydrothermal scheduling. Economic dispatch is the optimization process that determines the operation of the least cost connected thermal units. That means the units which are already on, which are producing power. How load should be shared among these such that the cost is minimum given the total electric demand and the minimum and maximum for operation limits of each generator. Whereas unit commitment is a process that determines the units that should operate for a particular load out of the total thermal units in the system, connected and not connected. The difference here between economic dispatch and unit commitment is that unit commitment includes committing the off units, bringing in, starting up the units which have been off till a particular time, or shutting down the units if they are not required. The basic difference, therefore, between economic dispatch and unit commitment is economic dispatch is confined to already running generators. Unit commitment takes the all the units into consideration. Hence, it deals with the running cost and startup cost of a unit also, or shutdown cost of a unit also. The third one, hydrothermal scheduling, is the combination of hydro and thermal units towards the same objective for for achieving minimum cost. So basically everything is about load sharing with minimum cost. So before we proceed ahead, we need to have a knowledge on two aspects, two prerequisites are required here. First one is cost and incremental cost. The cost of power production of a thermal unit is given by Ci is equal to Ai plus Bipgi plus Dipgi square. Thermal unit means one combination of boiler, turbine and generator. So the cost of power production, which includes fuel cost, coal cost, and running cost, variable cost also, is given by Ci equals to Ai plus Bi Pgi plus Di Pgi square. So many rupees per hour. So the cost depends upon the power generation. There is a factor Ai, component Ai, which does not of course depend on power production. That is the minimum cost. Then the incremental cost. Incremental cost of a thermal unit is obtained by differentiating the cost with respect to the power generation of that unit. This incremental cost is equal to dou Ci by dou Pgi. It indicates the increase in cost of a unit for a particular increase in power output. You can see in this slide here the curves. First curve to the left shows the cost curves of different units. 5 units are shown here. Each generator, each unit may have its own shape. The curve has its own slope. You can see that 1, 2, 3, 4 M are different generators. The incremental cost is shown to the right side by the curve A. The right side curve indicates both cost and incremental cost. The right side curve diagram indicates B is the cost curve and A is the incremental cost curve. You can imagine if you differentiate Ci, which is given shown in this slide, differentiate it with Pgi, then you will get Bi plus 2 di Pgi. So that means your incremental cost curve is a straight line curve, y equal to mx plus c form, whereas your cost curve is a curve Pgi square component is also present. So this is the basic information which is obtained from the heat rate curves of thermal generators. So every unit has its own curve, which is shown like this, having different slopes, different Ai values, Bi values and Di values. And the second prerequisite required to understand the economic dispatch is optimization. Optimization is a mathematical procedure. It basically means either to maximize or to minimize. It depends upon the given function. If the given function is efficiency or profit, then optimization means to maximize. On the other hand, if the given function is losses or cost, then optimization means to minimize. So thus the optimization is a mathematical procedure to obtain the minimum or maximum value of a given function. So suppose there is a function f of x equal to x minus 2 whole square plus 1. Then differentiating this function and equating it to 0 gives the minimum value of f of x. Because you see, on to the left of this is shown the curve, the graph of f of x equal to x minus 2 whole square plus 1. It is a curve of V shape. It is having its minimum value as is shown in the figure uh, at x is equal to 2. At x is equal to 2, the minimum value y is 1. So the same thing we will obtain mathematically also. Coming to the right side of the derivation here, f of x is differentiated with respect to x. X is the variable, f of x is the function. Then you will get 2 into x minus 2, which is made equal to 0. Then you will get x is equal to 2. When you substitute this x is equal to 2 back in f of x, you will get f of x equal to 1. Thus, f of x equal to 1 is the minimum value obtained at x is equal to 2. You can see that this is the minimum value, because till this point the curve slope is decreasing, and after it reaches this point the decrease in slope stops, rather it increases. So this becomes the minimum point. So on that particular basis we have made this df of x by dx is equal to 0, change in f of x with respect to x is equal to 0. So optimization vocabulary. Your optimization problem consists of three things: the objective function f of x, which is the output you are trying to maximize or minimize, then variables x1, x2, x3, so on. Here the variable in our problem that we are going to discuss, that is economic dispatch, is power generation of each unit, Pg1, Pg2, Pg3, so on. Constraints. Constraints are equations that place limits on how big or small some variables can get. There is a limit to power generation, for example. Each generator, each unit, each boiler, each turbine has its maximum rating. You cannot use this unit to produce more power than its maximum limit, upper limit. Similarly, this equipment has the lower limit also, minimum limit, so that lower and upper limits are constraints. So your optimization procedure consists of these three things, basically your variables, constraints and objective function. Example for variables is PGI, power generation output. Constraints example is the limits on PGI. Objective function example is cost of power production, for example. Before proceeding ahead, let us discuss a few difficulties in power system operation, which are listed out here. One important difficulty is load is continuously changing. It is random in nature. You don't know what the load will be in the next minute, in the next hour, and next day. So it is based upon some load forecasting procedure, some estimate. You will have to imagine the load demand and generate the power using the available generators with you. Suppose always the generators available are more than required. With this assumption, if we proceed, then out of the available generators, many generators, how many generators are required at a particular time, and what should be the load sharing, how to divide the total load among the each generators. That is the subject matter of this discussion. The second difficulty that is obtained here is electricity generated cannot be stored in bulk, so it has to be dispatched then and there. That means when you are generating electricity in excess, for example, but you don't have the load, sufficient load, then the excess generated energy, you cannot store it. There are no possibilities, there are few possibilities. There is still research going in the area of power storage. So you cannot store it. Once you are generating means you have to dispatch the generated power so that it has to be met to the load. So you have to generate optimally what is required, irrespective of whether the load is changing or it is constant. Then the thermal power plant takes time to start. For example, you have four thermal units running in the presently. So then the next hour you expect that the load is going to increase. Then if you want that another thermal unit to be added, you cannot do so immediately, because the basic attribute of a thermal power plant is it requires some time to start. It cannot be started instantly. So that is the reason why generally thermal power plant is not used to take to meet sudden changes, sudden increase in load. Generally, hydro units can be started immediately. So, still, when you are planning generation, then you must consider this point that when the bulk power is increasing, then thermal power plant cannot be immediately started. Then state of the power network is ever changing. Like the load, the state of the power network, whether the network is a very complicated, complex connection of different transmission lines, they are connected through the buses, through the nodes. So once if one of the transmission line is out due to opening of a circuit breaker by a fault, then the network uh, network configuration changes. So that is how the state of the network is also changing always. The four aspects of power system operation. A power system operation operator will have to always remember these four aspects. The first one is safety, quality, reliability, economy. Then comes economy. In the same order, the importance is outlined. Safety, safety of not only the personal, the environment also. Environmental hazards, pollution should be minimum, and the safety of the equipment, the generators, boilers, and turbines in particular. So that is what we are going to stress here. Safety of the equipment is important. Then the quality, frequency and voltage output of the power generators should always conform to certain standards. You cannot allow frequency and voltage to change widely. There are some limitations on frequency and voltage deviations. So that you have to correct. Reliability. You should see that any break in the power supply is not there, because that will be not tolerable by both the supplier and consumer. Always the power demand should always be met by the power generation instantaneously. Always load and generation should match, like we have in commodity markets, the balancing of supply and generation, supply and demand. Then the last aspect is the economy. While ensuring safety, quality, and reliability, you should see that you generate power at minimum cost, so that you will have buyers. The transmission people will buy the power, will sell the power to the transmit. The generation people will sell the power to the transmission people through bids. So unless the power generation companies offer bids at lower cost, then there will be no buyers for them. So making the generation cost at a minimum is a very important aspect of power system operation. These are how to achieve these operation criteria. Safety can be achieved by protecting the equipment. Quality can be achieved by reactive power balance. One of the quality parameters is voltage. So voltage profile can be maintained through reactive power balance. Frequency is maintained. Frequency deviations are restricted by a device in the generating station called governor. Then reliability. Reliability is maintaining the balance between load and generation. Economy can be maintained by an optimum generation schedule to control the cost and environmental impact also. Although we are discussing in this series only the cost of, we are only minimizing the cost of power production. So how do you mathematically model these aspects? Safety can be represented in the form of equipment constraints. For example, PGI min less than PGI less than PGI max. See, this indicates that the power generation limits of and ith generator should not be exceeded. So every generator will have nameplate rating. It will contain the maximum power the generator can produce. So that is the PGI max. Similarly, there is a minimum power also, because, for example, boiler cannot temperature cannot be maintained unless boiler is run at a minimum power value. That indicates the PGI min. So this inequality has always to be maintained. Similarly, the voltage profile, which is the quality variable, can be represented in terms of reactive power constraints as Q minimum, where Q is reactive power. Q minimum is less than Q max. The reliability factor, which takes into account power balance, can be written as summation of PGI equals to PD plus PL. Summation of PGI means sum of the powers generated by n number of generators connected to the system. PD is the load demand. PL is the transmission loss. If transmission loss is not there, you have an ideal system, then the equation may become summation of PGI equals to PD, which is not the case actually. Most of the time there are losses as well. Finally, the economic aspect becomes our objective. It can be mathematically written as minimize summation of Ci of PGI, where Ci is the cost of producing power. This is called objective function. We have seen the expression of Ci, which is equal to Ai plus Bi PGI plus Di PGI square. So that should be minimized. That is our objective function. That is our target. So now, once we know all these optimization elements, we go for problem formulation. We formulate the problem as in terms of mathematical optimization as follows. The objective function is minimize Ci of PGI summation. Subject to the constraints, summation of PGI is equal to PD plus PL. Supply demand balance. Then second equation is PGI min less than PGI less than PGI max. Limits on power generation of a unit. Ith unit. Any unit. I means 1, 2, 3, so on. Q min less than Q max is the third equation, which is the reactive power constraint. The equation 1 here is called equality constraint, whereas equations 2 and 3 are inequality constraints, because there is no equality sign here, there is less than sign here. So the solution of your unit commitment, economic dispatch, whose problem you are stating here, can be solved by many methods. One Lagrangian solution method is discussed here. So let us start simple. Case 1 is economic dispatch without considering losses and inequalities. That means your inequality relation that we have seen in the previous slide is ignored here, and your PL loss is also ignored. So we will starting with this simple case, your objective function will look like minimize the summation of Ci of PGI, subject to the constraint is summation of PGI equals to PD. So this is your simple problem. Now this summation of PGI equal to PD can be written as PD minus summation PGI equal to 0, so that all the terms will lie to the right side of equal to, and to the left side of equal to sign, and right side is 0. Now the first step towards solution by the Lagrangian method is you have to write an augmented cost function, which includes the objective function element and the constraints together. So that will look like L is equal to Ci plus lambda into PD minus summation PGI. I repeat, L equal to Ci plus lambda into PD minus summation PGI. Ci we know is the cost of power production of ith unit. PD is the load demand. Summation of PGI is the power production of I, again number of generators, out of which ith generator is 1. So here lambda is the new element. Lambda is called Lagrangian variable. It is required here because Ci and Pd minus summation Pgi have different units. The cost of the unit of Ci is rupees per hour and the units for Pd and Pgi is megawatts. So here you are bringing lambda whose unit is rupees per megawatt hour. The unit of lambda is rupees per megawatt hour. So if it is multiplied with PD minus PGI, then rupees per megawatt hour multiplied by megawatt will give you rupees per hour. So your CI is also having rupees per hour unit. So the equation will be balanced according to units and dimensions. So with this new variable Lagrangian variable lambda, you have a new augmented cost function L whose unit is again rupees per hour. So the solution, as you know, will be given by differentiating this L with respect to PGI and equating it to 0. So dou L by dou PGI made equal to 0 will yield you dou Ci by dou PGI plus lambda into 0 minus 1. This when equated to 0 will give you lambda equal to dou Ci by dou Pgi. So that means when expanded your lambda should be equal to dou C1 by dou Pg1, that is equal to dou C2 by dou Pg2, so on. If you have 5 units, you will have 5 terms up to dou C5 by dou Pg5. That means this dou C by dou Pg we have already known that it is incremental cost. So the incremental cost of each generator taking part in generation in power production process should be equal to lambda. This condition is called equal incremental cost condition. This condition will give you the least cost power generation. In words, you can say that if you want the power generated to be of least cost, you should operate all the generators such that each of the generator has the same incremental cost. ICI is equal to lambda, in other words. Incremental cost IC1 should be equal to IC2, IC3, the number of generators you have, the number of incremental cost. All the incremental cost should be the same for achieving the least cost. Now here, if you expand CI, which is AI plus BI PJ plus DI, here in place of di I have used small ci pgi square. Then you differentiate it. Then your pgi is equal to lambda minus bi by 2ci. So each power generation expression you are getting here, power generation of unit 1 is lambda minus b1 by 2c1. Power generation of unit 2 is lambda minus b2 by 2c2. Power generation of unit 3 will be lambda minus b3 by 2c3, so on. This is how load sharing for minimum cost can be obtained if we ignore losses and inequalities. We have ignored inequalities here. In this process, your Pg1, Pg2, Pg3, one of these may exceed the generation capacity of the unit. So that is not desirable. We will see in the next session how this inequality, how this upper limit can be exceed in limit of upper limit can be controlled. That will be seen in case 2 and case 3. Thank you.